Thank you very much for your presentation. I know that my name is difficult. Well, this is my presentation. I will start this presentation born with the collaboration with two different states. One is my university, the University Jaime in Castellón, in Spain, and the other is the Material Institute of Aveiro in Portugal. When I stay in the Institute of Materials of Aveiro, I start this research about the photocatalytic power of the titanium thin films, and we think that functionalized with nanoparticles, this type of material will improve the photocatalytic properties. It doesn't work. Okay. Well, I have distributed my presentation in the introduction when I explain the importance of the functionalization of the surfaces. Well, we continue with the experimental part when we explain that how can I synthesize the titanium oxide thin films, and how can I functionalize with the silver nanoparticles, and the result for photocatalytic experience and the antibacterial antimicrobial experience that I use. Well, why is important to functionalize the surfaces? Well, it's really important because we need to create intelligent surfaces that are capable of protecting us, to helping to improve our ecosystem, or to protect us with the antimicrobial or bacteria. For example, we functionalize with this type of thin films that doesn't affect the transparency of the glass. That, for example, for the ceramic tails or for normal window is really important. We can produce a new property of the substrate without any change in the optical properties, in this case transparency of the glass. Well, what is important? Imagine that you are in a classroom like this, and in this glass you can put this type of thin films, and you can be able to eliminate, for example, all the bacteria or all the virus that are in the room. So imagine only for the effect of the light, you can eliminate these bacteria, or for example, you can eliminate these pollutants, or for example, contaminated. Would be protected? Yes, of course. This is the reality, and this is the aim of this research. Try to obtain this type of gases that protect us in other way. Well, how can I do that? Okay, with the method to synthesize this type of thin films is spray coating or spray pyrolysis. We prepare a precursor solution and we apply with a spray with a handmade method. How I use this method in compare with, for example, LED or physical vapor deposition? Well, this method is totally applicable for the industry. So if you talk with an industrial, as you say, that if your method needs, for example, high vacuum or something like that, probably it doesn't work, because the industry doesn't work with this type of methods. In this case, this is a type of method for produce the glass in the ceramic tails. So this method can be applied really easy in the industrial things. Well, we prepare a precursor solution with the titanium and with the ethanol. Why I use ethanol? Well, because the ethanol produces a better film in compare with water. Water have not good adhesion in this type of substrates. Well, we coating to form the crystallized titanium oxide at 500 degrees, and after we produce and post-annealing to grow or to increase the crystallization of this titanium oxide. Well, in this type of products, we only obtain the Anatase phase of the titanium oxide, that is the most photocatalytic phases of the titanium oxide. Well, how can I produce these silver nanoparticles? Well, the most industrial applicable method is using, for my point of view, the nanosecond laser. Well, what is this technique? Oh, well, it's pulsar acceleration in liquids that we applied the laser into a metal substrate, and with the pulse of the laser, we produce the side of the material. In this case, we produce silver nanoparticles that the color is yellow for this type of side. Well, when we have this dispersion, we apply it into the surface of the titanium oxide, and then coating with a lower temperature in compared with the titanium oxide. Why we use this temperature? Well, in order to try to add the nanoparticles on the surface of the titanium oxide. Well, we produce a post-annealing 2500 degrees in order to obtain this heteroreaction between the titanium oxide and the silver nanoparticles. Well, as you can see, the thin film are totally dense, no cracks are there, so the thin film are really applicable for this type. In other applications, you can see very clear the density of the thin films. Well, the thickness is around 300 nanometers. It's difficult to obtain all the same thickness in all the samples because it's a handmade method, but we can try to obtain regularity this thickness. Okay. When you see the transmission electron microscopy, in order to try to understand where are the nanoparticles in this thin film, because using the scanning electron microscopy, it's really difficult to find the nanoparticles on the film. You only can see the film and no more. Well, when we can see the thin film, we can see perfectly that in this part, the matrix, the matrix is only titanium oxide, and when you put in the nanoparticles over there the thin film, you can show very clearly the silver. That is really clear that the nanoparticles are on the surface of the titanium oxide. Well, using the Grazing incidence X-ray diffraction, Grazing incidence is the diffraction that we use when you are working with thin films. If you work with powder, you only use X-ray diffraction. Well, when we use Grazing incidence X-ray diffraction, we can see perfectly the peaks around the silver pattern, and of course the peaks related to the Anatase phase of the titanium oxide. Well, as we can see, there are the peaks with the silver oxide. Well, it's normal because we produce a heating in the nanoparticles, and the nanoparticles are not really stable with this type of products. So it's normal to obtain this cause of the temperatures. So it's not a problem because the photocatalytic property doesn't have changed for a little bit of oxidation of the silver nanoparticles. Well, when we study the optical property, we can see that the optical transmittance are really high, 85% or 80% in compared with a common glass, a window glass. So the application for a normal glass is really good. So the minimal decrease of the transference of the layer due to the addition of the silver nanoparticles. This type of transmittance is capable for the thickness. If you increase the thickness of the thin films, the transference decreases a lot. If you are, for example, for 500 nanometers or more, the transmittance of the thin films decrease a lot. So it's not applicable for a Windows glass, for example. Well, this type of oscillations that are not normal in the titanium oxide, as you know, the titanium oxide is totally white, so it's not normal, this type of absorption in the visual range, is created in the transmittance between the interference between the air film or the film substrate. It's not produced for the nanoparticles, it's not produced for the titanium oxide. It's only an interference that probably a physics can explain very well this type of process. Well, when we measure the optical band gap using the tau spot, it's not the change of the band gap is not too high. You have for the titanium oxide 3.7, and for the titanium oxide coated with the silver nanoparticle 3.7. Is it normal? Yes, because you are not doping the material. You are producing a heteroschotsky union, a Schottky barrier. You are putting the titanium oxide on the titanium oxide the silver. You are not coating into the titanium oxide the silver. So if, for example, the band gap change, probably the silver is not on the surface of the titanium oxide. It's into the titanium oxide in the structure. So this is not the objective for this work. So when we analyze the Raman analysis, we can identify really well that is only the Anatase phase, there's not the rutyl phase. That is really good because the rutyl phase decreases the photocatalytic properties of the titanium oxide. And it's normal that the modes doesn't move because for the silver nanoparticles, because it doesn't interact in the structure of the titanium oxide. So that is all correct. Well, how can I do the photocatalysis analysis? Well, we prepare a 30 milliliter of Rhodamine B. As you know, Rhodamine B is a normal pollutant. The color is rather powerful. It's a pink powerful. So we prepare 5 ppms, and the total weight of the catalyst is 0.9 milligrams. It's too low in compared with other works that are published nowadays. So we apply with the UV light. This is the type of light that you use, and we measure the degradation of the pollutant exposed to the UV light during 10 minutes for the first and 30 minutes afterwards in order to analyze how can I degrade the pollutant. Well, the difference between the titanium oxide thin films in order to compare the titanium oxide with silver nanoparticles is too high. Observe the times. In this case, only with the titanium oxide, you waste 30 minutes, around 6 hours, and the degradation is not total for the pollutant. But in the case that we put the nanoparticles on the surface of the titanium oxide, only in 200 minutes, the degradation is over 500%. So imagine the difference in the photocatalytic activity. So why do you produce the nanoparticles? Well, we study, of course, the kinetic of these types of discontamination, and as you can see, the photolysis, only the pollutant with the lamp doesn't affect for the photodegradation of the pollutant, and in compare with the only titanium oxide, in compare with the silver nanoparticles with titanium oxide, the difference is clearly the constant rate of the kinetic constant of the titanium oxide with silver nanoparticles is too high. One of twice as high in compare with the other. So how can I explain what is happening for this type of material? Because you are using these two materials, in this case the titanium oxide too, but the difference with the silver nanoparticle is really high. Well, we put different scavengers in order to explain how is the mechanism for this type of photocatalysis. So we put a hydrolysis scavenger, a vacancy scavenger, and superoxide scavenger in order to try to understand which species can degrade the pollutant. Okay, so in this case, when I use the hydroxyl scavengers, the reaction is too low. So, of course, all the reactive species are used in the photocatalytic process, but the most important one is the hydroxyl scavenger. So, with the collaboration with the Professor Tito of the Department of the Chemistry for the University of Aveiro, try to understand the possible scheme of the reaction. So the titanium oxide generate this electron pair separation, and the electron can jump for the electron valence, but the silver nanoparticles can accept these electrons in order to produce more reactive species in compare with only the titanium oxide alone. So this is the possible mechanism that the photocatalysis is really better in compare with only the titanium oxide alone. Well, the recycling study of the catalyst is mandatory in all the catalysis study. You need to know perfectly if your photocatalysis have the same activity for the time. In this case, the photocatalytic activity reduced only 5%, and this is normal because we study with FETIR these films after the photocatalysis analysis, and we observe that the Rhodamine B, the pollutant, are into the photocatalytic center of the material, so it's normal, and this decreasing is not really important in order to other decreasing that, for example, lose the 50% of the degradation activity. Well, in order to find another property of these films, we determination the antibacterial activity for this film with the light. We put Escherichia coli in the surface of this type of films and irradiate with UV light. But you know that hydroxide species are produced in this type of when you irradiate with the UV light. So probably, of course, the bacteria are dead with the time for the production of reactive species of UV light. And of course, the results are always mandatory. So the antibacterial rate is 90% when you apply the UV light with the titanium oxide with silver nanoparticles for the bacteria. So for the conclusions, it's possible to functionalize the titanium oxide using silver nanoparticles. We produce this type of these two methods that they are really applicable industrially, the spray pyrolysis and the production of silver nanoparticles, and the mechanism of the photogradation of Rhodamine B has been studied and concluded that the species involved in the reaction, the majority have drowsy radicals. So, thank you very much for your attention. Thank you for the opportunity for the Professor Carda to give me to this Congress. And thank you, of course, for the support for the project that we can be able to do this type of research. Thank you very much.
So thank you for the nice talk. Any questions? Please.
How can you produce the silver nanoparticles in the solution? In Grazing?
Yeah. Hey.
And the second one
Yeah.
is, can you show me this big one, big titanium oxide, and the small one is of silver coin,
Yeah.
and realize the OH, oxygen and hydrogen. Can you measure the pH acidic level? Can you measure?
Well, thank you for different questions.
Yes.
Yeah,
One
yeah.
question is the other and second question.
Yeah. Okay. The first question
Because
is like,
in the solution,
yeah, how can yeah, you put the metal, okay, in a bulk, okay, a thin film of the metal, and you apply with the laser to the metal, and
which metal?
for example gold, silver,
Silver?
yeah,
Silver. No.
yeah,
We want to make a silver
yeah,
nanoparticle
yeah.
and can use
You exchange the material
yeah.
with the laser,
Mm-hmm.
and for depends on the pulse of the laser, you can control the size of the nanoparticles.
But we can write to this
Yeah.
yes. The others, yes.
This is a femtosecond laser, okay?
I can
In this case,
in solution, nanoparticles in solution.
yeah, here,
Where is the metal?
here,
Oh, here. Can you use this?
yeah.
What's in the solution?
Water,
Water.
Yeah.
Water.
water. You have, for example, this article that explains this type of production of nanoparticles, and you have here an expert for this type of production.
Also the green wavelength is very good.
Yeah.
Because silver, copper, with the IR wavelength, they're highly reflective. But with the green, because of the plasma effect, they are much more absorbing, much less reflective, so it's very efficient. Especially with the femtosecond laser, non-linear effects, so you have much more absorption.
Why you use the solution?
Yeah, we do that also. We do this with a different laser. Now we're using the femtosecond laser. But it's a very efficient method to do this. And so it's very interesting.
Thank you. The others one go.
It's go?
The others.
It's not time. Oh.
Thank you. So quickly you can respond.
Ah.
Sorry, the others
See.
go to.
You are asking me about the transmission electron microscopy for the silver nanoparticles.
No. You can write the equation and realize the OH. Can you measure the pH or acidic level? So if you put inside the OH,
Yeah.
oxygen and hydrogen,
Yeah.
you must solve the acidic level. Or basic.
No, but it's not this species. It's a reactive species. It's the radical. It's not the anion hydroxyl. It's the reactive species hydroxyl. You know, it's the radical, not the oxide species. You know, you for example can measure with
Your equation is the
other part.
big ball.
Yeah, the big ball. Yeah, but
Yeah.
look,
The OH.
this is the radical.
Yeah.
The
But
point.
If you put inside the solution, you must see the acidic level.
No, it's the radical, not the hydroxyl. It's not OH with minus. No, it's not type of species. You need to. This is the reason that I put this type. For example, I put for hydroxyl scavenger, I put acid formic. No, sorry, terbutol alcohol. Because this species can scavenger this type of radicals. It's not an increasing of the pH because it's not the same species. You are confusing this type of species. It's not the enemy of the proton. No. It's a radical species.
Always radical.
Yeah.
It's a mechanistic representation. No?
Yeah.
Another thing is that it is real. No?
Yeah. I try. Of course, I say I try to explain this with these
No,
mechanisms.
It's conventional.
Yeah.